So we're very happy to have Christof Kuelske here from Wacom to talk about gradient Gibbs measures on regular trees. Thanks.
Yeah, it's great to be here and talk to you in Texas at the Groups and Dynamics seminar. So this will be a probabilistic talk, so don't hesitate to ask questions if you feel maybe uncomfortable with the objects. And so what is this going to be about? It's going to be about spin systems. And the spin variables will take values in Z, so in the integers or in the Q. So the base space is a regular tree, so where each vertex has the same number of nearest neighbors. In this case, it's the binary tree. And so we have 3 nearest neighbors, and this is actually a finite portion of the binary tree, but we would like to consider the infinite volume in our base space and have the infinite tree with d+1 neighbors. And so there will be a number of theorems and types of results. And for the most part, this is work with Florian Henning, who is also present in the audience. And so I will start with some existence results of Gibbs measures and also gradient Gibbs measures, and we will see what is the difference for gradient models, so for gradient specifications, where the energies will depend only on the jumps which configuration makes along the edges. And so, so there's one thing, it's about localized Gibbs measures. And this will be in a certain regime of parameters of the model, here described by a transfer operator, which amounts sort of intuitively to strong coupling. Yes, and I will be more precise about that. And then, so this is theorem 1, but then we will talk also about delocalized gradient Gibbs measures. So where these height variables will have unbounded fluctuations. So they are fundamentally different. And so this first part will be about spatially homogeneous measures. So that means that from any vertex, in particular, the single side marginals will be the same, but also the finite distributions on such a little subtree here will not depend which subtree I'm taking. Yes, so it will be even tree automorphism invariant. And so I will then come to the point which I was asked to by Chris to talk about mainly, namely about spatially inhomogeneous gradient Gibbs measures, and there's also some relation with a dynamical system which I would like to describe. And then there's also, so this is relatively new. It's a paper which is now accepted in Annals of Applied Probability with Florian, and then there's even a newer result. It's a different methodology in terms, it's more statistical mechanics flavor, and if I have time, I would like to describe this also. This is with a French team with Arnaud Ligny and Laurent Coquille. And so here are some keywords of methods which are being used. So we will need to talk about 3NX Markov chains and Gibbs measures, of course, and boundary laws and fixed points, but also things beyond the fixed point of certain maps. Namely, we will talk about stability analysis for nonlinear dynamical systems which play a role here. Yes. Okay, so let us start. What is a Gibbs specification on a tree? So we would like to describe statistical mechanics models as measures on infinite volume configuration. So infinite volume is V is now this vertex set of a regular tree. And so we have 2 sorts, main interesting cases of state spaces. One is the integers and the other one is this DQ. And so in principle, we could also be more general and take more general local state spaces. But for the purpose of the talk, I will take these 2 additive and abelian groups. Yes. And so in statistical mechanics, you would like to describe infinite volume measures, and you cannot write down formulas right away because it is you need to define things in terms of specifications. Yes. And so what is a specification if you're on a general graph? So that's a candidate system for conditional probabilities of an infinite volume Gibbs measure. And so here, a specification, what do you do? I mean, you take a certain finite subvolume. Let's say it's a tree, this little blue tree, and you specify what the conditional probability of the measure should look like for the random variables which are indexed by this finite volume if you prescribe all the outside. Yes. And so in this case, in the models we consider, you have what we call statistical physics a nearest neighbor interaction. Yes. And so the configuration omega lambda, a height configuration, let's say of integers here, enters via these weights q omega x omega y, which give you a weight which sort of couples the omega x and the omega y. And so first you have the edges here, which are in the interior of the lambda, but you have also edges which couple you to the outside. And the outside, these on the red dots, this thing here, you freeze the boundary condition, and so you get actually probability kernel. Yeah? So that tells you if I'm specifying everything here on the outside, what is the probability to see an omega lambda configuration in the inside? Yes. And so note this is nearest neighbor specification because we don't need to look further than along the edges, and we have the spatial Markovianness. So if the boundary condition is entering only through the immediate neighborhood, this outer neighborhood of the lambda. And so what is the Gibbs measure? A Gibbs measure is one which has the same conditional probabilities as the specified gamma lambda. And so this is an integral version to describe what this is. Namely, you take a test function f, and you say the measure mu is invariant if you first put in the f expectation here. Yes. You take this as a probability measure. You take expectation with respect to the degrees of freedom here. And then you randomize over the boundary condition, and this gives you the same as if you take the mu. So that means the mu is invariant under the action of these kernels, gamma lambda, like you have it in Markov chains. You have an invariant measure, but it's not only invariant under just one kernel, but a family of kernels, these gamma lambdas. Yes, and so these are the famous Gaussian-Lanford-Riel equations, the theory developed in the 60s and introduced in the 60s. So this is what is the Gibbs measure, and we shall be interested in Gibbs measures for such models here. And now I need to tell you about specifics for trees. Namely, there's a very nice notion which plays a huge role here about tree indexed Markov chains. I mean, so okay, we now know what is a Gibbs measure if you have such omega matrix. And so what is the tree index Markov chain? Everybody knows Markov chains in the discrete time if you have integers. And so on the tree, and intuitively it means the following. I mean, in reality, it means the following. So a measure is a tree index Markov chain is the following is true. So we single out a vertex. Let's assume that this measure looks the same from every vertex. So it's invariant under tree automorphisms. Yes. And then, so how do you construct can you get the measure? So you say it's a tree index Markov chain if you can get it by sampling the single side marginal. So just looking at the variable here. And if you are interested in what is happening here, then sample given the value of this marginal, which shall be a V. So let's say this is a little, this is a V, and this is a W vertex. Then you get the joint distribution of these two things by first sampling this one, and then sampling an omega W value given the omega V value according to this transition matrix. So this is actually a kernel. No? So if you fix this one, you sum over these ones, you get one. Probability kernel shall be a transition matrix, an infinite transition matrix. And you get the full measure if you go from the inside to the outside, and you get these two guys if you sample independently, given these two values to go from here to here. Okay, so there's also an abstract definition, what it means to be a tree index Markov chain. Namely, it goes like this. You take the tree, yes, here's the tree. So you single out some edge, and you take the edge with an orientation. Actually, you need to consider both orientations, this one and this one. Then you say, when do I have a tree index Markov chain? So I have this measure giving mass to these values of the random variables which are indexed by all the points. So I say this is a tree index Markov chain, or one says if the mu conditional on the sigma algebra of the past of V and W. So I simply only make a picture. I mean, so the past of an oriented edge are all the vertices which lie here. So the infinitely many, uncountably many. And so there's a sigma algebra generated by the degrees of freedom, by the spin variables all here. And so you say it's a tree index Markov chain if you take some event here, you take conditional expectation on the past, it only depends on the immediate past here. So that's the notion of a tree index Markov chain abstractly. And this means if this is true, you can describe it by this thing. This is effectively a transition matrix. Okay, so there's one abstract theorem which comes from a play with tail triviality in 0-1 law, and this is the following. So if mu is an extremal Gibbs measure, it is necessarily a tree index Markov chain. Okay, recall that the Gibbs measures are given by this formula. So this is a linear equation. So it's interesting to look at the extremal points and so the non-decomposable ones. And there's also a theory about extremal decomposition for Gibbs measures in terms of the extremals. And so in particular for trees, there's this relationship that extremal Gibbs measures are always tree index Markov chains, but not vice versa. So there are examples and straightforward examples, for instance, in the Ising model with the boundary condition where in a range of parameters, the opposite implication is not correct. Okay, so now we would like to talk about gradient models. So we take our infinite regular tree, so with vertices and edges, and d plus 1 nearest neighbors. One says that's the degree d of the tree. And so let's take Z as a local state space and call this height variable. So the infinite volume state space is d to the power v. So all maps from sites to integer configurations. And so before we had a specification on a tree, which was given by this matrix Q of omega x comma omega y. Let's now suppose that the Q of omega x comma omega y is actually a function. And also it's a symmetric function. So it depends only on the modulus omega x minus omega y. Which is, of course, an integer, and this is the increment. No? So this you call the increment, of course, along an edge. And if this is the case, you call it this a gradient specification. No? Okay, and note, of course, you have this invariance of this specification. So here's a simple picture. So symbolic picture. So here's your base space, no? So which is a tree effectively. But you could also formulate gradient specifications on other graphs, infinite graphs, for instance, the lattice CD. or even other ones. Then you have this local state space Z. And so an infinite volume configuration is like this. And so there's, of course, the invariance due to this formula that if you shift in the height direction, the boundary conditions, so these red points are supposed to mean the boundary conditions, then this thing has the same probability as this for the shifted boundary condition. So, you know, we have this invariant. And so now let me talk about, we already know what are Gibbs measures, right? So these are the solutions of the DLR equation. And but there are also gradient Gibbs measures which do not come from Gibbs measures. And so, but before, let me maybe give you some examples. So let's assume in the following that this transfer operator function, yeah, so which appears here and gives us the price or the degree of suppression usually that we have to pay if we make large increments. But let's suppose that this is strictly positive. There can be, of course, interesting examples where this is not strictly positive, yes, but supported maybe on finitely many points. But we suppose that it's strictly positive, and often it's from physics it comes in this exponential form. So with a parameter beta and some u of modulus I, it's a gradient interaction potential, and beta parameter is called inverse temperature. And famous examples, the most straightforward example is the straight line here, where you have u of I bar as the modulus, and this is called the SOS-model. It's much studied, also on the lattice and other graphs. You can have a square, it's called discrete Gaussian, but you can take a power, a general power. It doesn't need to be bigger than 1. So then, of course, it's not convex, but concave, but we don't care. So in our theory, actually, we don't even need monotonicity. So what comes later, it could look like this. We need that the zero is somewhat pronounced, somewhat a ground state. And of course, our aim is now to describe and construct infinite volume measures, no, like the Gibbs measures, which satisfy this DLR equation. And but there's some care needed actually. So there are these Gibbs measures, which are probability measures on the local state space to the V's in these things. And so these things sort of know the absolute heights, yes. So if you have a function which depends on these variables with the absolute heights, you can take expectations of it. And so there can be also interesting measures, which are the gradient Gibbs measures, where you forget about what the absolute height is. Yeah, and you consider only probability measures on omega modulo a joint shift z. Joint shift z, where you know, shift this thing in the height direction jointly, and consider only observables which are insensitive with respect to this joint height shifts. And then you can write this DLR equation. Skipping some technical details, you can write this DLR equation if you're looking only at such functions which have this independence with respect to joint height shift. And then it's important to know that, of course, if you have a measure on this space, you get in particular measure on the increments. Yeah, and a measure which can also take expectations of functions which are insensitive to joint height shifts. But the other thing does not hold. Let's say if you're interested in translation invariant or in automorphism invariant things, it is not so that, I mean, there are gradient measures which gradient Gibbs measures which do not come from Gibbs measures. So for instance, if you have the simple nearest neighbor random walk where you toss a coin and you go with plus minus in the plus minus 1 with probability 1/2, then you have an object which is, and you go do this also into the past, then you have an object which has nice increments, which are translation invariant. But of course, you have to pin this point somehow. No? So this is not coming from a translation invariant measure which would know the absolute height, yes. And so the purpose of this talk is to outline construction of this, first of all, in the spatially homogeneous case for localized measures, so corresponding to these ones, and spatially inhomogeneous, and also for localized states, but also I will describe things for non-localized gradient Gibbs measures, but in the spatially homogeneous situation. Yeah. Then I will also talk about these measures for homogeneous for an homogeneous model, which we always have. By this, I simply mean that the Qi do not depend on the edge. No? So this you could also make Qs which depend on the edge, but at first we don't do this. Yeah? But nevertheless, even if you have homogeneous interactions, we can have spatially homogeneous measures. Yeah. Okay, so here are some is the background transparency. So people have worked in mostly on the lattice, actually, over the last decades. And here's some names of people who've worked on this. And so it's also coming from statistical physics, popular to look at continuous height functions, yes, R-valued height functions. And on trees, so there's some people here, and also recent interesting preprint by Lermas Toninelli on this issue. And for the talk, so there's these two papers with Florian, and one automorphism invariant, one non-automorphism invariant, not even translation invariant. This is a precursor paper, also with Arnaud and Woodkear. And so this is an independent method from statistical mechanics by doing expansions and also getting extreme and inhomogeneous Gibbs states, at least in a subclass of models. So this is a subclass of models than the one which we have here. Okay. And so let me give you the first theorem. The first theorem is for localized Gibbs measures in the spatially homogeneous. And this for me is always, by definition, use of words the same as the say-tree automorphism invariant measures. Okay, so here we introduce some. I was saying in the beginning, so we are talking about strong coupling assumptions. So this we put on this transfer operator Q, which is something like the energy, and it describes the coupling. So it's something like the exponential of minus energy. And so we want that the D plus one, recall D plus one is the number of nearest neighbors on the tree. Half norm is finite, yes. So we will need to work in certain AP spaces, and so we essentially it will be interesting to work in the local state space Z and also ZQ, but so we also take away the zero and in both of these groups, and allow that S is one of these choices. Okay, and of course we need, because of the unboundedness of the variables, if we look how our model was defined. Okay, so my model was defined like this. Yeah. So we have Q, we have to take a lot of Qs, and these things are in principle unbounded, yes? And the Z is the normalization factor, which turns this into a probability measure. So it depends on these red points of boundary condition. And of course, the Q cannot be just anything to get a finite thing. This has to be summable over all the things inside, yes? Otherwise, this is not summable. And the condition is needed to make this to make this true, and this is the finiteness of this norm. Yes. Okay, and then
what's excuse me. So what is D in this case?
D is the degree of the tree, which is
okay.
so D plus 1 is the number of nearest neighbors.
Oh, okay, I see.
So this is, for instance, here it's a binary tree. D equal 2 means binary tree. And so, okay, so this is, and because if you have a lot of neighbors, somehow it's holding somehow the interface of this height variable more down, you know. If you just have 3 neighbors, it's holding you not so much down with the same interaction than if you have 30. So the D comes in some sense. And exactly, thanks for the question. And then, so we defined for any integer D, so for the fixed tree, degree of the tree, we define a so-called good set for the interactions. And this is defined in terms of 2 inequalities, which will become clearer maybe later. So this is, for the moment, it's just a subset of R2, of the positive quadrant of R2. So we have gamma delta. So we will have to substitute later certain norms, CP norms in this. And it's defined in terms of 2 inequalities, which have to be true. So they exist in epsilon bigger than 0 such that this is true and such that this is true. And for instance, if D is equal to, it's explicit, you can solve the inequalities and you get a picture which approximately looks like this. Yeah. And so then there's a theorem, namely that's the first theorem that we have. So we fix the degree of the tree. For instance, binary tree D equal to, or tree with arbitrary large D, fixed D. Then we assume that this interaction function Q, which punishes for us the increments, has a Q0 equal to 1. So there's a multiplicative degree of freedom in the whole definition. If I may go back here. I mean, if you multiply this with a constant C, the C goes out, you know, to get some power and it's canceled away in the partition function. So we can choose a normalization as we like. So we choose Q0 is 1. Yes. And so then we set these 2 parameters. Gamma is the D plus 1/2 norm on the full Z. Yes. So essentially, this thing has to be finite. Yes. So this has to be finite now. Yeah. So it should be smaller than infinity. And then we set the delta is the D plus 1 norm, but only away from the 0. Yeah. And so the idea is that the delta should be small. So if you fix the gamma, yeah, then here the delta needs to be smaller than this value to be in the good set. And so that means that actually the Q should be concentrated somehow, should resemble the indicator of 0, but otherwise there can be small things, of course, to make the model non-trivial. Yeah. So for instance, this can be achieved in this example of the so-called SOS model by choosing beta large. In any reasonable model, it can be achieved by choosing beta large. And so then it says, so if the Q doesn't satisfy anything else, it can be, you know, it can be wiggly here somehow. It doesn't need to be monotone or log of it convex or anything. So then there exists a family of distinct tree automorphism invariant Gibbs measures mu I. Okay, so they are equivalent. Okay, so we have mu i's, and the idea is they concentrate at the height I. No? So actually, you don't get very much new by considering different heights. It suffices. You get the full information if you only consider the height mu0, because you can get all these other measures by a joint translation of the local spin spaces in the height direction. So maybe if we recall this naive picture here, yeah. So these are things which are localized then somehow in the height 0. And you can, by invariance of the model in the height direction, you can move this also to any other height. So the idea, these are measures which are with large probability sitting on the 0, and occasionally, of course, they might make arbitrarily crazy things, but so they are everywhere on the tree. I mean, with large probability, they stay close to 0. And so we call them localized. And yeah, and so we also have some bounds, some explicit bounds. So if we're looking for the probability not to be at the height I, divided by the probability to be at I, so this should be a small number, and this is actually a small number in terms of the delta, which is the way how well the Q concentrates in the sense of p+1 norm on the one, and some other stuff which is also small if the delta is small, namely this epsilon gamma delta, and so this epsilon gamma delta is solution, the smallest positive solution to this equation here. So this is the offset delta, and this is this gamma epsilon d, which is a parabola in for d equal 2. And this, if the delta goes to 0, then this moves down, and this solution this also goes down. So this is so these are sort of concentration bounds from in the view of the single type margin. Yeah. So this is the first thing. And also we can consider a number of, I mean, we can also consider other groups as local state spaces, namely the group ZQ. For instance, here's Z5. I've made a naive picture, you know, 0, 1, 2, -1, -2. And so if we want to look at these type of models, then we take the analog of a gradient model, but in this ZQ space. Then we need to have that this transfer operator function is an even function on ZQ. So it looks naively like this. I mean, it can, so it still should be resemble very much the indicator of 0, and there can be some other stuff. So which needs to be small, and then you can write down the whole thing again. So this has to be replaced by ZQ and ZQ. And the same thing stays true, and then you're getting measures which are tree automorphism invariant, and so they will favor now one of these. For each of these states, you can get a measure which favors these things. And so these things have been called clock models because this looks like a clock with 5 hours, or discrete rotator models. And there's a very specific model, which is the Potts model, where you have a particular nice form, namely you have a bias to be 0. And for all the other values, you choose the same. So you don't care how big the jump is. So if you make a jump along an edge, that means you have to substitute this thing. And if you make a jump of 1 or 2, it doesn't matter, you know. And this is nicer, this model, and this is also solvable in the sense of solving with some tricks nonlinear equations, and you have more insight and explicit solution somehow. And so then, so there's another theorem about, this is actually the theorem of the second paper with Florian about these, no, sorry, this is now about the, still in the translation invariant setup, but the delocalized gradient Gibbs measure. So this is also interesting, namely, so suppose a little more, namely that Q is in a 1 of C. Again, strict positivity, maybe it's not needed, but we suppose it. Okay, so there's some reason why we do it, and things become so easier. And we still have this good two-dimensional good set, depending on the D, which looks like this in all dimensions. And if now this pair of the 1 norms, yeah, of course, this one is simply 1. This one is simply the number 1 plus this one, okay? But if this is in this good set, so it's a condition on the Q norm, on the 1 norm of the Q to be nice, then there exist also GDMs, gradient Gibbs measures, which do not come from localized Gibbs measures. So I recall to you, I mean, gradient Gibbs measures, which do not come from a localized Gibbs measure, look morally like this one. but everywhere on the tree. So they have a tendency to if you're looking at the sum of increments, they grow. And this is surprising that they can actually coexist. Huh? So for any, and it's so that for any Q, so you have gradient in the invariant GTMs coming from, now there's a new notion, boundary law solutions from Q periodic boundary law solutions. And these gradient Gibbs measures are not equal to the so-called free state. What would be the free state? Free state would be, you have this Q, yeah, which punishes you your increments, and for any edge independently, you choose a random variable according to the distribution of Q. So we didn't assume that the Q is normalized to be 1. So if you want this to be a probability distribution, you have to normalize it by the sum over the i's, which is the 1 norm. Okay. And so this is always actually a gradient Gibbs measure, and but there are more, no? So they're non-trivial ones. Delocalization in this sense means the following: is precise definition. So we are allowed in the gradient Gibbs measure nu to look at increments. So this is a measure not for the absolute height, but for the increments. And so if we fix 1 point, we are looking at the increment and sum to the next increment along a path. Then this thing converges. So the probability that we find this in a finite height k for every finite height k goes to 0. So this is a vague convergence of this measure. Of this to the 0 measure. No? So that means that this goes up. So and especially for the free state, you have simply a nearest neighbor. I mean, you have simply a random walk, not the nearest neighbor random walk, but with this distribution. Okay, and so the interesting thing is if you go also through the criteria, for instance, in the SOS model, so coexistence, so of GMs and GDMs, localized, delocalized ones, is possible for the same parameters. So you can compute ranges of parameters of betas where you can see that this is possible. All right, and so how do you prove such things? So there's this theorem, and now there's the notion of boundary laws coming into play. So that's a background theorem. There was an old paper, and it's a probability paper by Zachary. And it says there's a one-to-one relation between Gibbs measures, which are also tree-indexed Markov chains, and normalizable boundary laws. What's the boundary law? It's you're looking at the set of all oriented edges, and then you're looking at strictly positive measures on the local state space. Yeah, so it tells you, it gives you a certain weight to make an increment of 0, 1, 2, etc., -1, okay, -2. And so it has one multiplicative constant tree, so you take modulo multiplicative constants. And so such a prescription of this, of such, I mean, for every oriented edge, we have such these weights. No? And so they must satisfy some consistency and some normalizability. And the consistency, okay, normalizability, I will come to in the next slide. And if you have such boundary laws, which are good for the model, and they are determined in terms of equations and nonlinear equations, and they will be responsible for these discrete dynamical systems. Yeah, so then you can write down a Gibbs measure which is associated with these boundary laws, and it's given by a perturbation of the Q's. So Q are, so to speak, the free ones. And so if you're interested in the mu to see the finite volume marginal on a lambda together with the outer boundary. So what you have to do, you have to take everywhere you have a bond B, you take a product, and then you also have to modify things with the so-called boundary law. Yeah? And the boundary law is something that has a sort of, for the oriented edge has a foot point and a target point, yes? like this. And here the target point is the y lambda. So y is in the outer boundary, y lambda is the unique vertex in this oriented edge inside the volume. And then you put here the omega y inside this boundary law. Yeah. So this is you can take a label, no, a spin value, and you take it inside. So this gives you perturbation. This is sort of a Radon-Nikodym derivative of the free things here. And also you can write down what's the Markov chain transition operator, namely it is this one. So that's the transfer matrix, and then you have to modify things with a boundary law going sort of in the opposite direction. So with a target point here, you go from omega to y and so on. Okay, and this is normalization. Okay, and now what is the boundary law equations? So that's sort of the tree recursion that you. Also, people from physics have been written down, but let's say in proper ways here. So boundary law has to satisfy the following equation. So here we are looking at an oriented edge going from x to y, and so the boundary law takes a value I in the local state space in our groups. I mean in Z, let's say. And then you say it is a boundary law for this interaction Q if it satisfies this equation. What do you do here? You have the interaction, in general, can be a matrix again here, Qij, and you have to multiply with the incoming oriented edges starting from, let's say, Z1 and going to X, Z1X. Take the matrix product, and then you take the product over these things. And so this multiplicative freedom. So this has to hold at any oriented edge, for instance, also in the opposite one. So we have to look at this thing and for all the oriented edges on the tree. So this is in general a huge equation. Yeah. And so it's interesting to see what solutions it has and so on and so forth, and what you can say. So that's an analytic play with these kind of things, you know, in given models. On given classes of models. And so here's one thing, if you really want a Gibbs measure, yes, so you need a normalizable single side marginal. So here's some formula, yes. And if the boundary law is simply crazy and too big and not decaying fast enough, this is not going to give you the chance to have a single side marginal, let's say, even, which is finite. It's not normalizable. So you need something, and this is this equation. Yeah, so here you consider an X, and you consider as opposed to this one, you consider everything which goes into the same vertex. So this is a product over D plus one, nearest neighbors here, and this has to be finite. So you have to work in the appropriate spaces. So these things stay finite. Yeah. And so starting with. Let me start to give you some idea in this homogeneous localized boundary law solution business. I mean, to prove the first theorem that you have in the strong coupling regimes, these tree automorphism invariant things. So we're looking for the boundary law equation now for something which does not depend on the edge. So that's the first thing, to look at homogeneous solutions. So the lambda Zx will be a lambda, and the lambda xy will be the same lambda. And so then this means that this is all the same for all these things. So this is actually, because we always have d terms here in this thing, this is power d. Okay, it's a nonlinear equation, and it looks much better already, nevertheless. And so this, if you think a bit about it, this normalizability thing is satisfied if and only if the lambda is in some proper LP space, and this P is D plus 1 over D. It's easy to see. And so it's a bit maybe more convenient to go from lambda to X by using taking the D's root. And so since lambda is strictly positive anyhow, we can do this. And so then this corresponds to saying, so this corresponding object X has to be in the sequence space LD plus 1. And then we reformulate this equation, which is now the same for, therefore I need only to consider at one edge. And let's choose also the C in some way. I mean, there could be different choices. No? So one choice is to choose the C in such a way that the lambda of 0 always turns out to be 1. Or the x of 0 turns out to be 1. So we wanted to write this as an x to the d, and this is an x to the d, and then we take yeah. So then we can take away the so because this is to the power d, we can take away 1d. Yes, and so anyway, so it's possible without loss of information to rewrite things in the following way. So these boundary laws described now in terms of x, which are normalizable, they are fixed points of an operator. And let us consider things only away from the 0. So sequences sort of that are only considered away from the 0. And so the operator is the following. Yeah. So this is convolution Q with x to the power d. And we formulated it here to be on the full AP space to allow also for negative things, but effectively they will all be positive. So this is a convolution of x of Q with x to the d, and this is a normalization which keeps these things at 0 at the value I equals 0. Okay, so why do we get now these powers and d plus 1/2 and so on and so forth? So at least one idea. So we use Young convolution inequality in LP. Yeah, so we want this so in this paper, we really construct a self-map of a certain ball, of a d plus 1 ball. And so here we have convolution of Q with x to the d, and we want this to close somehow. So we need to work with a d plus 1. So this we apply for d plus 1. And then the v will be the x to the power d. And you have to choose a Q in such a way that we get something which again is expressible in terms of the x d plus 1 norm. And so this in turn then gives us a good choice of the p, and the p turns out to be this d plus 1/2. So anyhow, so I'm not going to all the details, but you get, for instance, this type of estimate. So which shows you that the Tx, so this new sequence Tx, x is the sequence in d plus 1, LD plus 1. So this is bounded by the d plus 1 norm of this thing. And then here you use the Young inequality and you get the Q d plus 1/2 norm, and you get here this power to the d. Now, if we assume that this thing is small, yes, and it had a name before, and this is small and had a name before, then we find if this is less or equal than epsilon to the d, yeah? So if the x is in an epsilon ball with respect to the d plus 1 norm, then this is also. We want to construct a self-map of this epsilon ball, and this is of course the case if this is smaller than epsilon. And if you look, this was one of the so this one was one of these equations, yeah, in inequalities that appeared in the definition of the group set. I mean, so this epsilon is the ball radius of the invariant ball, and you have this then with this d plus 1/2 norm and d plus 1 norm of the Q, then this is fine. Okay, and this is saying contractivity. No? So in order to see that this is a contraction, we have to work a bit more and play with the Young inequality, and this then gives us existence of fixed points. And then we can go through the machinery and get back to the measures with these formulas. And So this gives us these localized states. And I see that I have to speed up a little. Okay, so there's an interesting part which I can only briefly describe, namely, how to get these delocalized gradient Gibbs measures. So we said we were looking for nice D+1 normalizable boundary law solutions, or X solutions corresponding to boundary laws. And nevertheless, also other solutions can be interesting, namely those which are periodic in the height direction. Okay, so they can never be, if they are periodic, they can never have any finite p-norm. But nevertheless, they are relevant because if they are periodic, they give rise to these GDMs, which are not localized, yes. And so there's a nice theorem, and says if we let us build, let us go from the Z-valued model to a ZQ-valued model, and define an associated fuzzy transfer operator. I mean, define it from the Q in QQ. And then there's a formula which says, okay, suppose that you have constructed a proper Gibbs measure in this for this finite spin model. Then you get to a GGM. Yeah. So by first sampling for the finite spin model from the Gibbs measure which you have for this interaction, the value, and then doing an independent resampling of the values along the edges. So here there's, for instance, Q equals 3, and you are choosing along an edge spin variable here, you take the increment, so increment happens to be 1, and you resample then, conditional on this 1, which you got here, increments which are in the class, yeah, in the class, so they are, if this is 1 is in Q is equal to 3, there could be 1, 4, 7, etc. Okay. So this is also a nice construction, yes. And now, okay, because I don't have so much time anymore, so so I come now to the part with the non-homogeneous gradient states. Yeah, and its theorem goes like this, and it's in the second paper, in this which now got accepted. So consider a gradient specification, and suppose again that the Q is an L1. And okay, symmetry and regular tree with D+1 nearest neighbor. Then also there's the interesting theorem, namely, so no smallness assumption on the Q like we had before. There exists always a finite height period Q, which could be very big and could depend on the particular interaction, could depend on the degree, such that if you go even higher, so for higher periods than this one, there are always gradient Gibbs measures of a period Q. And so I said before, I mean, there's this construction, and if this a measure can be constructed in such a way, you say it's a period Q, a GGM. And it says, so there are always such measures which are not invariant on the translation of the tree. So they are not tree automorphism invariant, and moreover, they are not invariant under translation of the tree. They have this delocalization property, as I said before. If you're summing up the increments along a path, this thing doesn't localize, so you will never find at a fixed height k if you go far away this random this path here. And so maybe to flash a little at least. So what's the idea? To reconstruct non-homogeneous Gibbs measures on this ZQ state space. So this machinery which I described for you. We are trying to find some measure here which is not translation invariant, which is strange somehow, and do this somehow for general models nevertheless, and large Qs. So we cannot hope for computations or anything like this. And then if you have this, we put it into this machinery and get out some GDM. But and then we also have to prove this, if this thing is not automorphism invariant, this is not by any miracle swallowing up and creating something which is again tree automorphism invariant. No, it keeps the non-translation invariance. Okay, so in here maybe there's a little, nevertheless, some picture with this dynamical system to show. Namely, okay, so we had this full boundary law equation, for which we have to, in principle, to look at every oriented edge. And so let us look at least not for homogeneous solutions, but solutions which have some symmetry. And so we do the following thing. So here's a picture of the tree, which happens in this picture to be binary tree, or was it general. So if we fix some vertex and call it a root, or this one. And now, in principle, for instance, if we have to look at such a, we have to find out what this boundary law is. Yes, boundary law again is something which is associated to each oriented edge, and you take a value. It's positive measure modulo constants, and you put in here a value corresponding to the increments. So a value in the local state space. And then let us look for this nonlinear boundary law equation again. So if we want the blue thing, we have to know what the red incoming things are, the boundary laws. Let's suppose that they are the same. No? At least in this hierarchy, I mean, they are the same. I mean, so the immediate, let's say, parents, I mean, these are the two parents of this one, they do the same stuff. They don't need to be the same here. And so for all hierarchies, going back, you're looking for solutions where you have this sort of radial symmetry. And you have this one. And so here, then remember the boundary law equation had some C's appearing. So we simply choose a different normalization, which is the L1 normalization. And so since we are looking now for I in the Q, these are vectors, you know, of Q entries, and if you normalize, then you are on a simplex. And so this whole stuff, if you rewrite it, it gives you a map HQ, which takes you from a simplex, let's say, where these things live, to a simplex where these things live. The same simplex, of course. And then the idea is to find solutions which are going into the backwards direction, yes, namely as follows. So we know it's easy to see if you take equidistribution here, then this will be a fixed point. And so we do the following thing. We want to take something which is close to equidistribution and do the backwards iteration. So you can maybe do this a couple of steps, but maybe the backwards trajectories will move out of the simplex. But the idea is like this. I mean, so here's some symbolic picture. So here's this equidistribution, which is a fixed point. And suppose that you have an unstable space here, first of all, for the linearization of this map, and a stable space for the linearization. And then you have an unstable manifold and a stable manifold for this discrete dynamical system. And then, so if you're now starting on the unstable space, the two unstable states, and looking at the backwards trajectory, then you will converge to the equidistribution. And so the idea is actually to make sure that you have a positive dimension in this unstable space, unstable for the forward direction, stable for the backwards direction. And so then if you choose something which is not quite at the equidistribution, but a bit away from it, you have infinite backwards trajectories, which always stay, which look like this in the backwards direction, and converts to, yeah? So that's somehow the idea. And so in order to do this, we have to make sure, I mean, so we had here some help from Alberto Abandandolo that we can do this actually, that such theorems exist. So there are some technical issues also that we can have maybe neutral eigenvalues, and but we can sort of beat this thing. And so we get let's say this is the last slide. We harvest the following thing. So we do a linear analysis, yes, and lift it by the stable unstable manifold theorem, generalized stable unstable manifold theorem, and this gives us the following: for any degree of the tree, any height period q, if we have that there's a level tau for which the Fourier transform of the transfer operator, this one, so Gauss Fourier transform, satisfies the following condition. So this is a certain non-degeneracy condition. So this is just the L1 norm, and this is a D appearing. And so then that you have the strict inequality for some index j in 1 up to q minus 1. So then you find, so this is actually, where this is come from. It says that the unstable manifold of this HQ operator really has a positive dimension. So this turns out after computation to be related to the Fourier transform in this very nice way. And tau is a parameter you could think of 1. And if it's not 1, you can play a bit around it and vary it a little away in order to avoid degeneracies and neutral eigenvalues. So if you have this one, there are gradient Gibbs measures of period q which are not spatially homogeneous. And so here's some examples, very concrete examples. So in the SOS model, you take, so I recall to you, this is, so this is with this interaction. So let's say we are on the tree where we have 4 nearest neighbors. And let's say we're looking at period q equals 3 height periodic non-homogeneous gradient Gibbs measures, and then you can draw for different betas these lines. And the theorem says, okay, I have to be above this line when I sample the curve of the Fourier transform at this 2 pi over q times j, if I sample equidistantly. And if I'm looking for higher periods, then I'm sampling at denser points here. And so that means that also this beta, which is a relatively small one, feels like high temperature, but I'm also here finding some solutions. Okay, so this is the reason why this theorem works. And I am afraid I have to stop for the lack of time. But thanks for your attention.
Thanks. Let's see. I guess I'll stop recording.